Have you ever looked at a massive data set, or maybe a complex, seemingly infinite sequence of numbers, and just felt in your bones that there simply must be a hidden heartbeat behind it all?
Oh, absolutely. It's a very human feeling, isn't it?
Right, yeah. You look at this chaotic sprawl of digits, and they're just growing larger and more unwieldy by the second, and your mind desperately searches for a pattern.
We're wired for it. We look for structure in the noise.
Exactly. You think, surely nature doesn't just produce random noise at this massive scale. But often we're sort of tricked by our own brains into seeing patterns where none actually exist.
Like finding faces in the clouds.
Spot on, faces in the clouds.
Yeah.
But sometimes, very rarely, you apply exactly the right mathematical lens, and what looked like a chaotic ocean of digits suddenly resolves into this flawless crystalline architecture.
And that is exactly what we are looking at today.
Yes. Today, we are uncovering precisely that kind of architecture. So welcome to the deep dive.
Thank you. And what makes this particular architecture so compelling to me is that it's been hiding in plain sight for centuries.
Hiding where, exactly?
Well, we are talking about structures embedded deep within some of the most thoroughly studied numerical sequences in human history, namely the Fibonacci and Lucas sequences.
Which are legendary. I mean, mathematicians have scrutinized these numbers for, hundreds of years?
Quite literally centuries, pulling them apart, looking for every conceivable relationship, every hidden symmetry.
Right.
Yet, the framework we are examining today reveals an entirely new, fully deterministic engine operating silently right beneath the surface.
It's wild to think there's still uncharted territory there.
It is, but to see it, you have to look through a very specific, highly disciplined filter.
Exactly. And that is our mission for this deep dive. We are going to explore the final patched version. I want to be specific here. We are strictly looking at version 27.3.2 Saphi of the Tesla matrix framework.
Yes, developed by the independent researcher Antonio Víctor Salas Dual.
Now, I need to address the elephant in the room straight away. If you are listening to this and you hear the name Tesla coupled with the numbers 3, 6, and 9, your mind might immediately jump to, well, internet hyperbole.
Oh, the conspiracy forums? Yeah.
Right. You know the sort of thing. Mystical energy fields, secret frequencies of the universe, all that kind of rubbish.
We are stripping all of that away today. Completely.
We have to, because that's not what this is about.
Not at all. The work we are examining today is an exercise in rigorous mathematical discipline. It is about modular digital structures, strict integer arithmetic, and self-propagating recurrences.
So the Tesla name is just a nod.
Yes, the author uses Nikola Tesla as a conceptual inspiration, specifically his well-documented fascination with those numbers, 3, 6, and 9. But the actual mechanics of this framework are grounded entirely in hard numbers.
No mysticism.
None. There is no mysticism here. It is purely structural maths.
To make sure we stay anchored in that reality, let's just establish our sources for you, the listener. We are working primarily from Antonio Víctor Salas Dual's writings on his Substack, but the real core of our deep dive comes from the formally published bilingual Zenodo papers.
And again, we must stress this is the updated version 27.3.2 Saphi. The revisions matter immensely.
They really do. And crucially, this isn't just some theory floating around on a chalkboard somewhere.
Yeah.
We are also examining the accompanying public reproducibility package, version 27.2.
Which is absolutely vital to the credibility of the entire endeavor.
Why is that so important?
Because that reproducibility package contains the actual Python code. It has deterministic sieve experiments and demonstrative tables, all released under a Creative Commons license.
So anyone can just download it and test it themselves.
Exactly. It means we are dealing with testable deterministic computer science. The author isn't asking for blind faith from anyone.
He's providing the tools for independent verification.
Spot on. So we are going to be very precise today. We will be focusing on structural proofs and logical steps.
Right then. Where do we even begin with something this massive? Let's take the Fibonacci sequence as our starting point. It's famous.
Everyone knows the basics.
Yeah, you start with 1 and 1, add them together to get 2, add 1 and 2 to get 3, then 5, 8, 13, 21, and so on.
It stretches out into infinity,
creating these massive, towering integers. So if you are confronted with an infinite sequence like that, how on earth do you find a hidden matrix inside it? I mean, you can't possibly look at the whole thing.
Well, that's exactly it. You don't look at the whole sequence.
You don't.
No. And that is the first conceptual hurdle we have to clear. If you try to analyze every single consecutive number in the Fibonacci sequence looking for this specific modular architecture, you will simply be blinded by the noise.
Just too much data.
Far too dense. To find the structure, you have to make a surgical cut. You have to extract a very specific subsequence.
Right. And in this framework, that cut is referred to as a step 4 subsequence, isn't it?
It is.
Step 4, meaning we're going to jump through the sequence, skipping numbers.
Precisely. We are slicing through it at regular intervals. But, before we define the exact mathematical formula for that jump, we absolutely have to establish the ground rules of the indexing.
Oh, yes. The indexing rule.
Because if we get the indexing wrong, the entire matrix collapses before we even begin the maths. The Salas Dual framework strictly insists upon the one-based convention.
Let's unpack that for a second.
Wait.
Because one-based convention sounds quite a lot like software engineering jargon.
It is, mostly.
So if we're just talking about counting the positions of numbers in a sequence, why is there a debate at all? Don't we just start counting at 1? Like position 1, position 2, position 3?
You would think so, wouldn't you? But in the world of mathematics, and particularly in computer science, there is a massive, ongoing standardization debate about whether an index should start at 0 or at 1.
Really? 0?
Yes. A vast amount of modern programming languages, Python, C, Java, they all use a zero-based convention.
Meaning the first item in a list is at index 0.
Exactly. But Salas Dual's framework mandates a one-based convention. The first position is index 1, full stop.
I have to ask, why does it actually matter so much? I mean, if I have a line of apples on a table, whether I call the first one apple 0 or apple 1, it's still the exact same apple, isn't it?
It is physically the same apple, yes. But its mathematical relationship to all the other apples completely changes depending on its label.
How so?
Well, when we start applying modular arithmetic later on, which relies heavily on division and remainders based on the index number itself, a shift of a single digit changes every mathematical outcome downstream.
Ah, I see. So the maths actually breaks.
Completely. If you try to run this framework using a zero-based index, the modular rhythms we're going to discuss simply do not align. The symmetry fractures entirely.
So for the Lucas sequence, the first number, L sub 1, is 2. The second number, L sub 2, is 1. We definitely start at 1.
Yes, index 1. Always.
All right, so we are counting like normal humans, 1, 2, 3, 4. With that absolute rule locked in, how do we actually execute this step 4 cut?
Well, we are trying to isolate what the paper calls FiboTeslas and LucaTeslas.
Let's start with the FiboTeslas.
Right. The FiboTeslas are denoted in the paper as Ft sub n, and the formal definition is beautifully simple. It states that Ft sub n equals F sub 4n.
Okay, let me translate that. So Ft sub n equals F sub 4n. In plain English, to find our new FiboTesla number at any position n, we go to the original Fibonacci sequence, take that position n, and multiply it by 4.
Exactly correct. Let us work out the first one together.
Sure.
To find the first FiboTesla, Ft sub 1, you multiply the index 1 by 4, which gives you 4. So the first FiboTesla is simply the fourth Fibonacci number.
Okay, if you're listening, you can probably map this out in your head right now. The standard Fibonacci sequence, starting at index 1, goes 1, 1, 2, 3, 5, 8, 13, 21. So if we need the fourth number, position 1 is 1, position 2 is 1, position 3 is 2, position 4 is 3.
There you go.
So the first FiboTesla, Ft sub 1, is the number 3.
Exactly. Now, let us define the other branch, the LucaTeslas, denoted as Lt sub n.
This is where it gets a bit tricky, right?
Slightly. Their extraction formula introduces a vital shift. The definition is Lt sub n equals L sub 4n minus 1.
Ah, okay. Let me look at that. So we multiply the index by 4, just like before, but then we take a step backwards. We subtract 1 from the index position.
Yes. Let us calculate the first LucaTesla, Lt sub 1.
I'll do it. So you take the index 1, multiply by 4 to get 4, and then subtract 1, which gives you 3.
Exactly. So Lt sub 1 is the third Lucas number.
Okay, let me calculate that. Now, the Lucas sequence is a close cousin to Fibonacci, right? It uses the same rule of adding the previous two numbers together, but it starts with different seed values.
Yes, it starts with 2 and 1.
Right, so it goes 2, 1, 3, 4, 7, 11, 18, and so on. So position 1 is 2, position 2 is 1, position 3 is 3.
And what does that mean for our LucaTesla?
It means the first LucaTesla, Lt sub 1, is also the number 3.
Exactly. And this is where the underlying elegance of the entire framework begins to reveal itself. Think about what we just discovered.
It is quite striking.
Why does this specific slightly offset slicing matter? It is definitely not arbitrary. The first FiboTesla is 3. The first LucaTesla is 3.
They begin with the exact same numerical value.
Yes, but they originate from entirely different index positions within their parent sequences. One is the 4th Fibonacci number, the other is the 3rd Lucas number.
So they share a starting value, but their roots are planted in entirely different soil. That is, well, it's mathematically quite poetic, isn't it?
It is. It's a profound structural convergence.
Let's list out a few more of these raw numbers just to get a sense of how quickly these two new branches actually grow.
Let's do that.
For the FiboTeslas, jumping by 4 steps each time in the parent sequence, the raw numbers go 3, then 21, then 144, then 987, and they just explode upwards into the thousands and millions very quickly from there.
They grow exponentially, and for the LucaTeslas defined by that 4n-1 formula, the sequence goes 3, then 18, then 123, then 843, again, scaling up incredibly rapidly.
Now, I have to push back here for a moment.
Please do.
If I am looking at these two massive parent sequences, Fibonacci and Lucas, and I decide to just aggressively jump through them, picking out every fourth number or every fourth number minus one aren't I just mangling the sequence?
Mangling it.
Yeah. Isn't it like ripping out every fourth page of a novel, binding them together, and claiming you've discovered a brilliant new story? I mean, of course, it looks different. You've completely ignored most of the book. How is this mathematically sound?
That is a very natural objection, and it's one a lot of people have initially. Whenever we discard data, we risk losing the narrative, to use your literary metaphor.
Exactly.
But I would argue that comparing an infinite mathematical sequence to a novel doesn't quite capture the mechanics at play here. It is much more like using a stroboscope to observe a spinning wheel.
A stroboscope. Okay. I like a good analogy. Explain how that works in this context.
Imagine a wheel with complex geometric patterns painted on it, spinning so fast that the patterns just blur into a solid, chaotic gray disk to the naked eye.
Right, like looking at a fan blade.
Exactly. The information, the pattern is still there, but your frequency of observation, your continuous unblinking sight, simply cannot process the structure. It's too fast.
Okay, I follow that.
Now, if you flash a strobe light at the precise frequency of the wheel's rotation, say, illuminating it for a fraction of a second exactly every time it completes a quarter turn, what happens?
The wheel suddenly appears to stand perfectly still.
Right. Or maybe slowly rotating backwards, depending on the exact timing. But the point is, you haven't physically altered the wheel.
No.
And you haven't destroyed the information of its spin. Instead, by selectively filtering your observation, by pacing it to a very specific mathematical interval, you have revealed a hidden geometric alignment that was entirely invisible in the blur of continuous data.
Oh, wow. That is a brilliant way to conceptualize it.
The step 4 slicing in the Tesla matrix is the stroboscope. It freezes the sequence at precisely the right moments to reveal a structural truth that the full continuous sequence obscures.
We aren't ignoring the data at all. We are tuning our frequency of observation to match a hidden harmonic within the sequence.
Spot on.
But looking at these raw integers we just listed out, 3, 21, 144, 987 they still just look like fast-growing numbers to me. I'm staring at the frozen wheel, but I really don't see the grand geometry you were promising here.
Well, that's because the geometry only becomes visible when you apply the Tesla-inspired lens. The numbers themselves are too raw. We need to look at their internal properties. And that brings us to the concept of digital roots modulo 9.
Right. This is a crucial pivot in our deep dive. We are moving from the raw extraction of these numbers to the actual analysis of them.
Yes, the diagnostic phase.
The paper talks extensively about a heartbeat modulo 9 and these digital root vibrations. As we promised at the start, let's firmly define what the paper actually means by the word vibration, because that word carries an awful lot of baggage.
It does, and we must be fiercely clear about this to avoid any misunderstanding. In Salas Dual's framework, vibration is strictly a conceptual label.
Right.
It is a shorthand for a digital root read modulo 9. There are no mystical energy fields at play here.
No frequency healing.
No cosmic vibrations, none of that. It is pure classical modular arithmetic. The term vibration is used heuristically to suggest an internal numerical signature repeating over time, much like a mechanical oscillation in an engine.
I really appreciate that clarity. So let's break down the actual mechanism. What exactly is a digital root modulo 9? Because if someone hasn't taken a university number theory class, modulo arithmetic can sound incredibly daunting.
It sounds daunting, but it is actually deeply intuitive. Modular arithmetic is often called clock arithmetic.
But clock arithmetic.
If it is 10 o'clock in the morning and I tell you we have a meeting in 4 hours, you don't say the meeting is at 14 o'clock.
No, I'd say it's at 2 o'clock.
Exactly. You mentally wrap around the 12-hour face of the clock and realize the meeting is at 2. That is modulo 12 arithmetic. You divide by 12 and keep the remainder.
Right. So modulo 9 simply means we are wrapping around a clock face that only has 9 numbers on it instead of 12.
Precisely. And in base 10 mathematics, the standard decimal counting system we use every single day, finding the modulo 9 value of any number is mathematically equivalent to finding its digital root.
Okay, remind me how to find a digital root.
It's very simple. To find the digital root of a number, you simply add its individual digits together. If the result is more than one digit, you add those digits together again, repeating the process until you are left with a single digit from 1 to 9.
Okay, let's put this into practice. So we take the stroboscope we just built, which froze our sequence into these FiboTeslas and LucaTeslas, and we put a modulo 9 filter over the lens. Let's see what happens.
Let's take the FiboTeslas first.
Right. The raw numbers were 3, 21, 144, 987, and so on.
So apply the digital root process.
Okay, let's do this live.
Right.
FT sub 1, which is 3. Well, the digital root of 3 is just 3.
Correct.
Now, FT sub 2, which is 21, we add the digits. 2 plus 1 equals 3. So its digital root is 3.
Very good.
FT sub 3 is 144. 1 plus 4 equals 9. So its root is 9.
And the fourth?
FT sub 4 is 987. Let's walk through this one. 9 plus 8 is 17. 17 plus 7 is 24. We have 2 digits, so we add them again. 2 plus 4 equals 6, so the digital root is 6.
Exactly.
If we keep doing this, grinding these massive numbers down to their single-digit roots, what pattern actually emerges? Because so far I have 3, 3, 9, 6.
If you continue that exact calculation indefinitely, pushing into Fibonacci numbers with hundreds or thousands of digits, the FiboTesla digital roots reveal a perfect, unbreakable 6-beat cycle.
Really?
Yes, it goes 3, 3, 9, 6, 6, 9, and then it repeats 3, 3, 9, 6, 9, forever.
Oh, wow.
No matter how astronomically large the integers become, their underlying vibration in the step 4 branch is locked entirely into that 6-beat waltz.
That is genuinely staggering because the parent Fibonacci sequence feels so wild and expansive, you know. It's swelling into the billions and trillions. Yet underneath it all, hidden inside the specific step 4 cut, there is this incredibly calm, steady rhythm. 3, 3, 9, 6, 6, 9.
It is a remarkable hidden structure.
But what about our other branch, the LucaTeslas? Does it have a heartbeat too?
It does, and applying the digital root reduction here is equally revealing. Let us take the raw LucaTeslas we found earlier. 3, 18, 123, 843.
Okay, let me do the maths on these.
Go ahead.
The digital root of 3 is 3. The digital root of 18, 1 plus 8 is 9. The digital root of 123, 1 plus 2 plus 3 is 6.
And the next one?
The digital root of 843. Right, 8 plus 4 is 12, plus 3 is 15, and 1 plus 5 is 6.
Spot on. Now, if you map out this entire branch to infinity, the LucaTesla digital roots follow an overlapping but shifted 6-beat cycle.
This should help.
It goes 3, 9, 6, 6, 9, 3. And then it repeats indefinitely.
Let me just look at those 2 cycles side by side for a moment. FiboTesla, 3, 3, 9, 6, 6, 9. And LucaTesla, 3, 9, 6, 6, 9, 3.
You see the relationship?
It really is beautiful. These entirely untamed integers completely collapse into such a disciplined, closed-loop rhythm. And it's absolutely fascinating that both cycles consist exclusively of 3s, 6s, and 9s.
Yes.
It's really no wonder the author felt compelled to name the matrix after Tesla, given his famous quote about the magnificence of those specific numbers.
It is aesthetically very pleasing. It feels almost designed. However, this is exactly where we must exercise intense mathematical vigilance.
Why is that?
Because while both cycles look wonderfully symmetrical, they contain the exact same numerical components, just arranged in a slightly different order, there is a profound danger in simply admiring the symmetry and stopping there.
A danger. In symmetry.
Yes. In mathematics, symmetry is quite often a superficial trait that masks a much deeper functional asymmetry. If you look too closely at the mirrored beauty of these sequences, you will completely miss the actual machinery of how these numbers function in relation to prime candidates.
And this brings us to the absolute crux of this deep dive, doesn't it?
It does.
This is the V27.3.2 safe patch. This is the moment where we discover the vital asymmetry of the LucaTeslas. Because I look at those two cycles, and my human brain immediately thinks, oh, brilliant, they're perfectly balanced mirrors of each other.
Which is a very natural assumption.
But this final patch explicitly states, hold on, look closer. They aren't mirrors at all. One of them has a very specific structural job.
Precisely. This is arguably the most critical revelation of the entire revised paper. We must look specifically at the LucaTesla branch, the LT branch, and analyze how its internal vibrations map onto what number theory calls candidate residues.
Okay, let's slow down and define that. What exactly is a candidate residue, and what does it have to do with prime numbers? Because up until now, we've just been talking about sequences and modulo 9. How do primes suddenly enter the picture?
To understand this, we need to look at how prime numbers are distributed among all the other integers. Historically, finding primes, numbers divisible only by 1 in themselves, is computationally exhausting.
Right, because you just have to check them one by one, basically.
Exactly. But centuries ago, mathematicians realized that prime numbers are actually subject to certain structural constraints. Specifically, when you use a modulo 6 sieve, every single prime number greater than 3 must sit at very specific residue positions.
Modulo 6 now.
Namely, the positions where a number modulo 6 equals 1 and where a number modulo 6 equals 5.
I want to make sure I grasp this perfectly. You are talking about the classical 6k plus or minus 1 rails, right?
Yes, I am.
Okay, let me explain that for the listener. If you take any integer k, multiply it by 6, and then either add 1 or subtract 1, you create two distinct numerical tracks or rails.
Spot on.
And every single prime number in existence, aside from 2 and 3, lives somewhere on those two specific rails.
Yes. Now, not every number on those rails is a prime. You will definitely find composite numbers sitting there too. But if a number is not on those rails, it is mathematically impossible for it to be a prime. Those are the candidate slots.
Think of it like checking the designated VIP seats in a theater. You know the VIPs, the prime numbers, can only sit in those specific seats. There might be some regular people sitting in the VIP section too, but you know for an absolute fact you don't need to check the balcony or the back rows. You only search the candidate slots.
That is an excellent way to conceptualize it. Now, returning to the Tesla matrix, the strict correction from the final patch is this. When we map the LucaTesla branch against these VIP seats, we find a profound asymmetry.
Tell me.
In the LucaTesla cycle, the designated candidate slots are exclusively occupied by the vibrations 3 and 9.
Wait, let's look at the cycle again. The digital root cycle for the LucaTeslas is 396693.
Yes.
The number 6 happens twice in every single cycle. If 3 and 9 are occupying all the candidate slots, what on earth is the 6 doing?
It is structurally present. It is part of the sequence, an unavoidable output of the integer arithmetic. But the crucial asymmetry, the revelation of the patch, is that for any index in greater than 3, the vibration 6 never occupies those prime candidate slots.
Never.
Never. It never sits in a VIP seat. It is entirely excluded from the functional role of carrying prime candidate values.
Okay, I want to try an analogy here to see if I'm understanding the underlying physics of this mathematical system.
Yeah.
And I want to be clear to you, the listener, that this is purely an analogy and not a physics claim.
Of course.
Think of a mechanical engine. If you have perfectly symmetrical wheels spinning, well, that is very pretty to look at. But a perfectly symmetrical wheel doesn't drive a piston.
No, it doesn't.
Working engines require asymmetrical timing. You need compression and combustion firing at very specific staggered intervals.
Yes, if combustion happens everywhere evenly or at the wrong moment in the stroke, the engine simply seizes. The power comes from the asymmetry of the cycle.
Right. So some parts of the engine exist simply to provide the structure, the timing, the physical weight to keep the momentum going, while other parts, like the spark plugs, carry the actual load of combustion.
I see where you're going with this.
In the LucaTesla cycle, the 6 is the chassis. It is the heavy flywheel. It is structurally absolutely necessary to maintain the 6-beat rhythm. It spaces everything out, but it is not holding the combustion. Yeah. The 3s and the 9s are the spark plugs. They're the only ones firing in those prime candidate slots.
Your engine analogy is incredibly apt here. It perfectly illustrates why the V27.3.2 safe patch is so vital to the integrity of the framework. It demonstrates that asymmetrical rules are what give mathematical systems their functional depth.
Wait.
If the 6 were occupying candidate slots alongside the 3s and 9s, the entire predictive filtering architecture of this matrix would just collapse into noise.
You wouldn't be able to predict anything.
Exactly. The 6 is not merely decorative, it maintains the rhythm, it spaces out the sequence, but it deliberately stays out of the way of the prime candidate occupancy. It is a highly differentiated internal behavior.
So let's take stock for a moment. We have these two sequences, the FiboTeslas with their 33969 heartbeat, and the LucaTeslas with their asymmetrical 39669 heartbeat, where the 6 acts as a structural spacer.
Correct.
They seem like two fascinating, distinct entities. We've proven they have different internal mechanisms.
Huh.
But how do they actually relate to one another? I mean, are they just two parallel tracks running through the mathematical forest, never touching?
Oh, they are inextricably linked, and the mechanism that links them is essentially the mathematical linchpin of the entire paper.
Really?
Yes. It is an algebraic identity known as the Salas Dual bridge.
The Salas Dual bridge. Okay, what is the architecture of this bridge? How do you connect two infinite sequences?
The bridge is surprisingly elegant in its simplicity. It states quite simply, LT sub n equals FT sub n minus FT sub n minus 1.
Let me process that. You were saying that a LucaTesla is just the difference between the current FiboTesla and the previous one?
Yes. The LucaTesla represents the exact delta, the distance, between two consecutive FiboTeslas.
Let's test that right now. If you're listening, grab a pen or just follow along in your head. Let's take index 3.
Okay.
FT sub 3, the third FiboTesla we calculated earlier, is 144.
Yes, it is.
The previous one, the second FiboTesla, FT sub 2, is 21.
Correct.
So the bridge formula says we simply subtract them to find the LucaTesla. 144 minus 21. That gives me 123.
And what did we determine LT sub 3 was?
Exactly as predicted, 123 is LT sub 3, the third LucaTesla. The structure just snaps perfectly into place.
It is entirely robust across the entire infinite sequence. And the profound implication of this bridge is that the LucaTeslas are derived directly from the delta between consecutive FiboTeslas.
They are the steps.
They are the exact mathematical steps you must take to climb from one FiboTesla to the next. And because of this incremental relationship, the bridge leads us directly to what the paper calls the telescoping corollary.
The telescoping corollary. That sounds like a piece of Victorian navigational equipment. What does it actually mean computationally?
It means that if you want to find the value of any given FiboTesla, say FT sub n, you don't actually need to calculate it from the parent Fibonacci sequence at all.
You don't.
No. You can simply calculate the sum of all the LucaTeslas from index 1 up to index n. In mathematical terms, FT sub n equals the sum of all LT sub k, from k equals 1 to n.
Wait, hold on. If every FiboTesla is just the accumulated sum of all the previous LucaTeslas, does that fundamentally change how we view these two parent sequences?
It reframes them entirely.
Does it mean the Lucas sequence acts the genetic building blocks and the Fibonacci sequence is just the completed organism? Like, is the LucaTesla the DNA sequence, the incremental instructions for growth, while the FiboTesla is the fully grown body?
I agree with your conceptual framing there, provided we keep it firmly in the realm of metaphor.
Sure.
Analytically, it proves that these are not merely parallel roads. One sequence is computationally accumulating the increments of the other. The LucaTeslas are the generative building blocks. The FiboTeslas are the running total of that generation. They're bound together in a structural symbiosis.
You cannot have the FiboTesla body without the LucaTesla DNA.
Precisely.
That is it's incredibly satisfying to think about. We take these two sequences that mathematicians have studied separately for hundreds of years, and this matrix proves they are essentially locked in a master-builder relationship.
It is a beautiful revelation.
But practically speaking, I see a massive logistical problem here.
And what is that?
Well, if I want to calculate the 500 FiboTesla, I surely don't want to have to calculate all 499 previous LucaTeslas and add them up.
No, you wouldn't.
And I certainly don't want to calculate thousands of raw Fibonacci numbers just to execute my step 4 stroboscope cut. We're talking about integers with thousands of digits. How do you generate these massive numbers efficiently without just crashing your computer?
This is exactly the logistical problem addressed in the revised manuscript. And this brings us to the restored section 7.2 of the paper, which details what is known as the 7 engine.
The 7 engine. Again, the branding in this framework is absolutely top-notch. It sounds powerful. What does this engine actually do?
It is the computational heart of the framework. Section 7.2 outlines an internal, self-propagating recurrence. It allows you to calculate the next number in the sequence using only the 2 previous numbers without ever needing to reference the parent Fibonacci or Lucas sequences again.
Oh, wow. So you break free from the parent sequence entirely.
Entirely. The formula is beautifully concise. Ft sub n plus 1 equals 7 times Ft sub n minus Ft sub n minus 1.
Okay, so to find the next number, you just multiply the current number by 7 and subtract the previous one. And let me guess, the identical formula works for the LucaTeslas.
It does. LDC sub n plus 1 equals 7 times Lt sub n minus Lt sub n minus 1.
Let's walk through a cycle to hear the engine purr. We need 2 starting numbers to prime the pump. Let's use the FiboTeslas. We established earlier that Ft sub 1 is 3 and Ft sub 2 is 21.
Let's run the engine.
To find Ft sub 3, the 7 engine says we take our current number, 21, and multiply by 7.
Okay.
7 times 21 is 147. Then we subtract the previous number, which was 3. 147 minus 3 equals 144.
And there it is.
Ft sub 3 is exactly 144. It's an exact gear mechanism.
It is flawless. And we must emphasize why this is so remarkably powerful from a computational standpoint. This recurrence relies purely on exact integer arithmetic.
Why is integer arithmetic so important? I mean, most computers can handle decimals and fractions just fine, can't they?
They can, but computers handle decimals using what is called floating point arithmetic. And floating point maths is essentially an approximation.
An approximation.
Yes. When you deal with massive numbers or complex division, floating point maths introduces tiny, microscopic rounding errors. Over millions of calculations, those tiny errors compound into a floating point haze that completely destroys structural precision.
So the maths gets fuzzy.
Exactly. But the 7 engine uses only multiplication and subtraction of whole numbers. There are absolutely no decimals. There are no division operations that might result in fractional values.
Meaning there are 0 rounding errors.
0. The sequence builds itself exactly, perfectly to infinity, restricted only by the memory limit of the machine running it.
And it builds itself entirely independently. Once you have those first 2 numbers, 3 and 21, you never have to look at the original Fibonacci sequence ever again.
You don't.
You can just let the 7 engine run in a closed loop. It turns what was a passive observation, us shining a stroboscope at the Fibonacci sequence from the outside, into an active, self-contained computational object that generates its own reality.
Precisely. It is entirely self-sufficient. However, the revised patch includes a critical clarification regarding spatial movement that we really must address here.
Spatial movement.
Because the 7 engine is so incredibly efficient, it is very easy to lose track of our scale. When you fire up the 7 engine and make a jump to the next Tesla subindex, say, moving from Ft sub 3 to Ft sub 4, you are making a jump of 1 within the Tesla framework.
Right, just 1 tick of the engine.
But the paper clarifies that a jump of 3 Tesla subindices corresponds exactly to a massive jump of 12 indices in the original parent Fibonacci or Lucas sequence.
Ah, okay, I see the danger there. Because we're using the 7 engine to zip along our bespoke extracted branch so effortlessly, it's easy to forget how much ground we are actually covering in the parent sequence.
Yes.
A jump of 3 in our Tesla world means we just skip past 12 massive Fibonacci numbers. We are wearing 7-league boots here. We're covering immense mathematical distance with every single step.
Quite. The engine allows us to traverse the mathematical landscape at an extraordinary pace, while remaining firmly anchored to exact integers, which leads naturally to the final and perhaps most important question of our entire deep dive.
Right. What is the actual utility of this traversal?
Exactly.
We have this flawless, self-generating, deeply structured engine that dances to an unbreakable 369 heartbeat. But where does it actually drive us? What is it used for? Because up until now, this has been a brilliant piece of structural anatomy. It's beautiful, but how does it interact with the rest of mathematics? Does it solve a problem?
It projects outward into the deterministic filtering of prime candidates. The internal modular rhythm of the 369 vibrations connects directly to its external application along those classical 6K plus or minus 1 rails we discussed earlier.
Okay, let's return to the VIP seats. We know primes only sit on the 6K plus or minus 1 rails, But as you mentioned, those seats aren't exclusively filled with primes. There are composites numbers that look like primes but are actually products of smaller primes sitting in those seats too.
Yeah.
How does the Tesla matrix help us sort the true primes from the imposters?
The framework explains how composite columns, that is, the columns of numbers that sit on the rails but are not prime-act as periodic families, these families are induced by prime masks and what is known as CRT, or Chinese remainder theorem, composition.
Hold on, you can't just drop the Chinese remainder theorem into the conversation without breaking it down. How does CRT actually mask out the composite numbers? What does that mean mechanically?
Let us use a gear analogy. Imagine a series of interlocking cogs of different sizes. One cog has 5 teeth, another has 7 teeth, another has 11 teeth.
Okay, I'm picturing it.
If you mark one specific tooth on each cog with red paint and start spinning them, it will take a very specific, predictable amount of time for all those red teeth to align perfectly again.
Because they're all spinning at slightly different rates due to their sizes.
Precisely. The Chinese remainder theorem allows mathematicians to predict exactly when multiple periodic cycles, like our spinning cogs, will intersect or align based on their remainders.
Okay, I follow the cogs. How does that apply to composite numbers on our rails?
Every prime number creates its own cog of composite multiples. The number 5 creates composites every 5 steps. The number 7 creates composites every 7 steps.
Right.
These composite numbers land on our 6K plus or minus 1 rails in highly predictable, overlapping periodic rhythms. The Chinese remainder theorem allows the Tesla matrix to model all of these overlapping cogs simultaneously.
So the matrix doesn't just hunt for primes blindly.
No, it maps the cogs, it identifies the exact structured rhythms of where the composite numbers will land, allowing the algorithm to mask them out efficiently.
So to be completely clear here, we aren't saying the Tesla matrix magically spits out prime numbers like a vending machine.
No, absolutely not. And Antonio Víctor Salas Dual does not make that claim anywhere in the paper. The Tesla matrix is an incredibly structured pre-filter.
Pre-filter.
Yes. It uses the predictable 369 modular behaviors, the vibrations, the asymmetry of the 6 in the LucaTesla branch, to deterministically sort and filter the candidates on those rails before heavier computational prime checking algorithms even need to be run. It identifies the structural regularities of the composite so they can be bypassed.
It is a way of mapping the structural noise so you can ignore it, leaving only the prime signals behind. And this is where the theory truly hits the pavement for me.
How so?
Because anyone can write a paper claiming they've found a new, elegant way to look at prime numbers. The internet is full of unproven mathematical theories. But this paper comes with receipts. The Zenodo package.
Yes, the public reproducibility package, version 27.2, which is fully compatible with the v27.3.2 safe paper. This is a crucial element of the entire endeavor.
Tell me exactly what is in this package. Because in a world full of theoretical mathematics that exists purely on chalkboards and behind academic paywalls, how significant is it that the author essentially hands you the keys and the code to the engine?
It is immensely significant. It grounds the cinematic elegance of the 369 rhythm firmly in the realm of reproducible computer science.
So what do you get?
If you download the Zenodo repository, you aren't just getting theoretical PDFs. You receive actual Python code implementing the Tesla matrix framework. It contains deterministic sieve experiments that you can run on your own machine. It includes highly structured, demonstrative Excel tables.
That's incredible.
And all of this is released under a Creative Commons BYNC 4.0 license, meaning it is open for non-commercial research and educational use. It practically begs for independent verification.
It's an invitation. Here is my 7 engine, here's the stroboscope, here's the Python code, run it yourself, test my maths. It moves the conversation from abstract philosophy to testable engineering.
Yes, it does.
If I run that Python code, what am I actually going to see on my screen?
You will see the deterministic pre-filtering algorithm sorting the composite columns using the Chinese remainder theorem composition we discussed. You can verify the step 4 extraction yourself. You can track the digital roots.
Can you see the asymmetry?
Most importantly, yes. You can verify the asymmetry of the LucaTesla branch. You can watch the code prove that the vibration 6 actively avoids the prime candidate slots, just as the v27.3.2 safe patch claims. It is all right there in the compiler.
It's remarkable. We have covered an immense amount of ground today, driving deep into a framework that completely reframes how we look at sequences we thought we understood.
We certainly have.
Let's try to summarize this intense journey we've been on. We started by taking a vast, chaotic data set, the infinite Fibonacci and Lucas sequences. We applied a strict one-based indexing rule, realizing that a single shift in index changes the entire modular universe.
We then took our mathematical stroboscope and made a precise step 4 cut, extracting the FiboTeslas and the LucaTeslas, proving that they originate from different index positions but share identical starting values.
We applied the Tesla-inspired modular lens, reducing these massive integer branches to their digital roots modulo 9, which revealed the unbreakable 369 vibration cycles.
And crucially, thanks to the final patch, we recognized the vital asymmetry of the LucaTesla pairs. How the number 6 acts as a structural chassis, a heavy flywheel, leaving the candidate slots free for the 3s and 9s to carry the computational load.
We then crossed the Salas Dual bridge, proving algebraically that the LucaTeslas are the generative DNA steps between the fully formed FiboTeslas.
We fired up the 7 engine, demonstrating how the system self-propagates through pure, exact integer arithmetic without ever needing to reference the parent sequences or deal with floating point errors again.
And finally, we saw how this entire internal architecture projects outward, acting as a deterministic pre-filter for prime candidates along the 6K plus or minus 1 rails, mapped by the Chinese remainder theorem and entirely backed by reproducible Python code in the Zenodo package.
It is a profound structural alignment. It demonstrates that chaos is often just order waiting for the correct mathematical frequency of observation.
It really does change how you look at the numbers. It reminds you that even in systems that seem entirely mapped out, heavily scrutinized for centuries, there are hidden layers, hidden engines, waiting to be discovered if you apply the right lens.
Absolutely.
Which leaves me with a final, slightly provocative thought for you to mull over as we finish up. If a modular lens as specific as the Tesla matrix can reveal an entirely self-contained deterministic engine operating silently within Fibonacci and Lucas, two of the most heavily studied sequences in human history, you have to ask yourself, what other classical mathematical structures are currently hiding massive, undetected architectures?
It's a fascinating thought.
What other infinite sequences contain pristine, closed-loop geometries simply because we haven't found the right numerical rhythm to listen for yet? What else is hiding in the noise?
A brilliant question to end on. The architecture is out there. We simply need the discipline to see it.
Beautifully said. That wraps up our deep dive into the Tesla matrix. Thank you for joining us, and keep looking for the hidden heartbeat in the data.